Let's look at this example. Use logarithmic differentiation to find dy dx of y equal to the square root of the product of x squared plus 1 and x minus 1 quantity squared. So just as above, take the log of both sides. So you get ln, let's go ahead and bring it all the way over so we have space. So ln y equal to ln of that root, and then you expand it out just like we did before. X squared plus 1, x minus 1 squared. Okay, so that's equivalent to ln y equal to, and that'll be a half. And then you end up with ln x squared plus 1. And then plus 2 ln x minus 1, because you can bring down that 2 as well, right? And you could distribute that half if you want and simplify. I don't know what I did actually. So let's differentiate, and it actually works out nicer. So differentiate both sides now. Wait, what am I missing? I'm missing a logarithm. Oh no, they're there. Okay, we're good. Okay, we're good here. So now differentiate both sides. Okay, so you get 1 over y times y prime equal to, excuse me, a half, and then these derivatives, you get the 2x, 1 over x squared. So 2x, and then you get the x squared plus 1, right? So it's 1 over x squared plus 1, and then the times the derivative of 2x, or x squared plus 1, which is 2x. Plus, now that'll just be 2 over the x squared minus 1. Like that. Close the bracket. Okay, so now let's go ahead and distribute that 2, and it'll be a little simpler. So you get just x over x squared plus 1 plus 1 over x minus 1. So let's go ahead and add this up. LCD is that product. And that way we can simplify it a little bit further. So you get 1 over y prime equal to x times x minus 1 plus x squared plus 1 all over x squared plus 1 x minus 1. Add that up, and you get, so you get x squared minus x, so it ends up being 2x squared minus x plus 1 all over x squared plus 1 times x minus 1. Multiply through by the y. So y prime is equal to y times all of that. And I'm going to go ahead and make use of my technology. Bring that over here. And so then you just substitute for y. I mean, you got your y here if you want to just substitute. I'll go ahead and show that just to have it. So why is all this mess here? So you can take that and substitute. So I will, actually. Take that, duplicate it. That's going to go here. Take that, which I just copied. Duplicate that, and that's going to times that. Oh, I like how it does it, huh? Okay, so I'm going to actually take off the highlight because it doesn't look good. Okay, so that's what I substituted like that. doesn't really matter. Often they'll tell you to write it all in terms of x in the end. But it's not a big deal. It's easy to do that last substitution. Technique, though, definitely need to know it. Log of both sides, differentiate, solve for y prime. That's the concept. Okay, let's look at some integral formulas for logarithms. All right, so basically you have the integral of 1 over u du is equal to ln absolute value of u plus your arbitrary constant. That's just straight from the definition, really. But we are assuming stuff's positive, so you got to put the absolute values in there. So let's look at some examples. Well, I have two examples. One is indefinite integral and one is a definite integral. So let's look at this. Let's do the integral of tangent x dx. And we haven't done a lot of, well, you would have done tangent, but this is another way to show it, I guess. So you have the integral of, and so write tangent as sine x over cosine x dx. Okay, so then let's do your u substitution. We're going to let u equal cosine x so that du is minus sine x dx, or I like to write du is over -1 is equal to your sine x dx. So your sine x dx is what you're substituting for directly. So here's your sine x dx, like that. Here's your sine x dx. Okay. And so we replace that with your negative sign. So that equals then negative integral of 1 over u du, right? I mean, there's your u. Let's change the color on that. There's your u. And then your sine x dx becomes your du right here. And then I just take out the negative. So that equals negative ln absolute value of u. Didn't like that. You did. I'm sure you didn't either. Absolute value of u plus c. Now substitute back for your u, and you have minus ln absolute value. And what was u again? Oh yeah, it's cosine. Cosine x plus c. So that's the antiderivative of tangent, or at least another form of it, I guess. Let's look at another one. This is a definite integral. So evaluator find the definite integral from -1 to 0 of 3 over 3x minus 2 dx. So when you don't see any powers down here, it's just linear in the bottom, in that denominator, then you know it's going to be natural log. So you still got to figure out your integration constant. So you got to pick your u to be that 3x minus 2, and those 3's will actually cancel out real nicely. We will see. So we're going to let u equal that 3x minus 2, and so your du is 3 dx, or du over 3 is equal to the dx. So we replace the dx over here with du over 3, and then you'll see those 3's will cancel. So it works out pretty slick. So this is equal to the integral of -1 to 0, 3 over u, and then du over 3, and then those are gone. And so you get the integral of -1 to 0 of 1 over u du, and we know what that is. That's ln absolute value of u. And then you're going to evaluate that from x equals -1 to x equals 0. So since it's x originally, right, back here, way back here, this is x. So you can put in your x equals and x equals. So I'm going to put the u back, is what I like to do. So we're going to put the u back. So u, what was u? Oh yeah, 3x minus 2. So that's going to be ln absolute value of 3x minus 2. And then we're going to evaluate from -1 to 0. And then the variables match, so we're good there. Don't have to indicate what they are now. And substitute in and simplify. So ln absolute value of -2 minus ln absolute value of -3 minus 2. Good thing we have absolute values in there, or we might have some problems. So ln 2 minus ln 5, which is equal to ln of 2/5. Oops, I wrote a 3, didn't I? Let's put that back over here. So that's equal to ln of 2/5. Whatever that is. I don't really care what the actual decimals are. I want to see the exact form, please. Okay, so exact form. When you go on to physics and your engineering classes, then you can start doing approximations. Okay, that wraps up that section. We do 2.3 next on exponential functions, and then we skip 2.4, and then we do the rest of the chapter.